Apart from that, the plan for today is to see if we can make sense of classical logic and what the difference is. And if we have time, we'll also do the quantification, so talking about all elements of a given type, some element of a given type. But let's start with classical logic. That's also part of the coursework. So you have seen last week with Connor and Georgie that.
Sorry, have you got the Zoom?
I'm OBS recording because I don't. Oh no, I do have internet. Okay, so maybe you'll do it. But yes, thank you. So you saw last week how we can represent certain logical statements in type. It's talking about implications and conjunctions and disjunctions. And then there were some, you proved a lot of simple things, such that A and B implies A, and so on, right? But there's some statements that you might remember from the school years that you didn't consider. So these are the ones we're going to consider today. We get to see that they are not going to be universally valid. So here's one of the first ones that we're considering. It says that for any P, which perhaps foolishly is quantifying explicitly over, either P is true or not P is true. Remember that this was our symbol or. So that's something you might remember from logic, right? But what would it mean to actually prove this, as in writing a program that has this type?
So I can just ask it slightly.
Yeah.
That's the same. Is that the same as having a function to the top type?
This is the same as having a function from
but the whole thing to the top type. You're saying it's true. Is that the same as having a function to the top type?
It's the same as saying having a function from the top type.
From the top.
Saying that assuming you have only true, nothing else,
you can prove it.
You can prove this. And then a function from the top type, from the unit type. The unit type is exactly one element. So a function from a one element type to something else
shows it's something else.
It's just the same thing as something else, right? So there's no information in getting an argument of unit type. Because even before I give you that argument, you know it's going to be the only element that can exist in the unit type.
Yeah.
Yeah, so in general, I'm going to say that I can prove this if I can give an inhabitant of that type. So here I started to prove this by saying I claim that I have a function, and now all I have to do is fill in the right-hand side.
Have we already seen that it uses braces on the left-hand side to override default implicits?
If we haven't, we see it here now. So you see that this P here is implicit, but I want to talk about it explicitly, so I'm introducing it on the left with another pair of braces here, which is sometimes useful. Okay, so how would I prove this? Any ideas?
Start by Control-C, Control-Comma. See what the actual deal is.
Fine. I can also try Control-C, Control-A, right? No solution found, okay. Okay, so what's the deal? So we know that P is a set, and the goal is to either produce something with P or something of not P. So if I do Control-U before I do that, that's going to normalize this fully, and we see that this negation was defined to be the same as P implies the empty type. Import that so that it's not qualified under. Either P or not P. P implies not P. Okay. How do I prove something in a disjoint union in this type?
Through the injection of both sides.
On either side.
On either side, sorry, yeah. Inject on one and inject on the other.
So the only way to give something of this type is to either give something of this type or something of this type. That's why we use it to represent logical order, because you have to say this one or that one. And you have to be explicit about which one you want. So here I have to decide either that P is true or that P implies bottom. But I don't know what P is. All I know is that P is a set. But I'm asked to decide if P has some inhabitant or if it's empty. And that's not something I can really do, right? Because we don't know what P is.
And even if we did, yeah, I mean, so yeah, there's sort of two problems here. One of them is that not only do we not know what P is, we have no way of finding out.
Yeah. I mean, for specific P, you can do this, right? If P is the natural number, you can go left. You can give your favorite natural number, which is 42. And if P is empty, then you can go right, and you can give your favorite and only function from the empty type to the empty type, which is the identity function. But in general, for an arbitrary P, we have no way of finding out if it's empty or not.
So P could be the set of proofs that are given Turing machine points. And then this function would have to figure out whether it holds or not. That's what it's got to tell.
If we could do this, we could solve the whole thing.
Yeah. Yes. And that would, of course, be involve looking at P to see what P is to decide whether it's true or false. But actually doesn't let us do that mathematical sense. So we can't even look at P. So in fact, this type is extremely residential. It says everything sight unseen is either true or false. And the only way we could possibly prove that is to come down on one side or the other. So we'd either be saying, in effect, all propositions are true, or we'd be saying, all propositions are false. And I don't really want to live in a world where either of those situations, because things are going to get messy pretty fast. So for one, I'm really glad this type is uninhabited.
Please extend so what I would say right now to you're currently implementing a version of logic within a program. Can you even extend this so that it does have more to do with it?
It's possible, and it's interesting. It's not at all trivial.
Okay.
And it's not very well behaved in general.
And the question is, what do you lose, right? So our problem here is that when you see this disjoint union type, you are being promised a bit, right? You're at least being promised to know whether we went left or right. That's one bit of information. And that bit has got to come from somewhere. And there's nowhere for it to come from. So one of the reasons, the law of the excluded middle is just great in a Boolean logic situation. Like when you're talking about, when you're talking about bits, because there's no problem to say something which is already a bit is definitely either 0 or 1. That's so appropriate logic for those circumstances. Whereas here we're playing a completely different game, and it doesn't work out the same way. And that's okay.
Okay, Connor, do you want to try and prove this principle?
I can have to go.
Explain it first, of course.
Yes. So this mysterious DNE is called double negation elimination. You can see it says if you have not P, then you can deliver P. So, it's you can't prove to me that fairies don't exist. Where's my fairy? Right. Okay, so let's see what happens when we try. Again, Control C, Control comma. Oh, I hit the Control key for once. Right. Okay. Actually, that's what we really have. We've got a thing that promises us that there's no way anyone who proves P is false, it's lying. But does that mean we can actually extract a proof of P? So you asked me to do this one because it's full of non-ASCII characters. Whoops. I'm going to call this NNP because I can type that. Right. Okay, so my only chance. So there's nothing here. There's nothing that spits a P out, right? And there's, I've got nothing that I can plug in this hole that actually delivers a P. So my only chance really is to prove that this can't be happening to me. So I could try with NNP question mark. If I could figure out some input to feed to NNP, then I'd get a proof of false. So I'd be laughing. Okay. But now my goal is not P. Okay, fine. And now I have to prove false, and I've got a proof of P. I know one way to prove false. I can use NNP. Oh, I've done that thing again. Oh, but no, I have to prove not P. Oh, cool. That means I can get a proof of P. Okay, now I've got two proofs of P, and I have to prove false. You get the impression that it was funny because all I wanted to do when I started was prove P. And now I've got proofs of P coming out my ears, but I have to prove not P. It's just, life can be so cruel sometimes.
So it seems like this is also not possible to prove. Impossibility of something, you can actually get some evidence for it. And you can try and reason in the same way, see that, well, this is not going to work and there's nothing else you can do. But if you want to be a little bit more precise in your argument, then you can try and show that you can reduce your problem to something else. So here we have done this the other way around. Should we do the question, please?
Yeah, it's actually, so we've already figured out that len is impossible. So it's good to show that if we had dn, you would get len.
Yes. So that's
and that is really the fun one. Also, it's good to talk about.
yeah.
Yeah, so the idea, you might think, okay, dn is going to work because if I know how to squash any rumors that P is false, that could be because I secretly have a proof P in the back pocket. And all you need to do is take it out. But there might be other ways to show that P is false than to actually have a proof P, so that not P is false, than to actually have a proof. That's the trouble. it's not necessarily the case that any proof of this secret. Get out. Yeah, we're now going to be sure.
So we argue that this one, if you could solve this one, you can solve the multiple. If you know you can't do it. So now we're going to show that we can reduce this problem to this problem. So how do we do it? Well, what do we have? So we want to show P or not P. And we're assuming that we can remove double negations. Okay, an idea? Well, we know that a direct attack is just not going to work, right? Because then we get stuck. So we can't, no, sorry, that's nonsense. But up here, we knew that the direct attack would not work because we can't decide if we want to go left or go right. But this principle says that, well, you don't have to prove it directly, it's just enough to prove not the thing you want.
Yeah.
So let's see if we can do that. So the thing I want is P or not P.
Figure that out.
I guess so.
Yeah, so the double negation elimination here is really useful because it says, okay, actually, you don't have to prove P or not P, you just have to show that that's false.
And now we can,
You got the curly braces in there, they say that ignoring implication thing.
they're saying again, that's, so the type of DNE here is capital DNE, which was first argument is implicit argument. And here I'm supplying that implicit argument explicitly.
Yeah, so we're saying we are using double negation elimination explicitly for the proposition P or not.
And I think counter reflect that.
Yes, because that's the goal anyway.
I can infer that
You
for
understand the same thing, just say that. Actor will say, oh, well, P must be the goal. You know, if it's trying to figure out what P is and, you know, and you're proving something, and you're proving P with it, then okay.
Okay, so now we can just stop thinking for a little while, right? Because we are introducing a function.
Okay. Yeah. And then the rule of the game here is that one person is in charge of proving false, and the other one is in charge of proving things that aren't false. So who's going to be the operating system? Who's going to be the fun-loving criminal?
I think you're criminal.
Okay. So you're the operating system. Okay. So proving false is a bit like being an operating system. Because you know you can never actually pull me up, prove false, and leave. So you have to figure out how to keep on distracting people forever. That's what operating systems do. And what you've got in your context, if you're lucky, are some potential distractions. Like things which are negated propositions. You could, so when you're trying to prove false and you've got some negated stuff, then you can cause a distraction by invoking any of the negated stuff. So there's only one negated thing available.
That's going to give me false if I give it something.
Yeah, it's a bit like saying, okay, here's Fred is saying, as an operating system, I'm going to tag that process. So now it's my group. No, it's just like, no. Okay, now here I need to decide if I can win. But even if I can't win, I can always give control back to the operating system. I think it's inch 2, isn't it? With a subscript 2?
Yeah.
Right, I've played this game before. I know that if I go left, I'll be asked to prove P. Whereas if I go right, I'll be asked to prove not P. And that's much better for a reason I'll show you. So that's inge, and then it's what, backslash underscore 2. So, okay, I go right. Okay, now I have to prove not P, which is really P implies false. So that's fantastic because because I get, you can tell it's a double act between Fred and me because there's lambdas and backslashes. See, if I go lambda p arrow question mark, I achieve great progress because two things happen. On the one hand, I get given a proof of P, and on the other hand, I get a control back to the operating system.
Okay, so now I have to prove bottom. Right? Do I have any way of proving bottom? Yes, I do. I have this thing, which, if you give it something, eventually it's giving it back a bottom. So I'm going to try that. And then you could say, well, now it's just going to be this infinite loop again, right? Because you tried that before, didn't you?
Well, let's see.
But let's see. Because now I guess I give back control to you.
Yeah. Now, okay, last time I tried to do this process, I went right. This time, I said, oh, sorry. I went left. And now, well, proof of P, but I got one last time. Classical proof is basically bank robbery.
What's going on there?
So when you're trying to prove false, anytime somebody gives you a hypothesis one search branch, you get to keep it. I mean, this is. It actually does make computational sense in a sort of twisted sort of a way. I'm trying, the sort of operating system analogy is kind of fair enough. So that there is actually a genuine way of managing concurrent programming and kind of switching between processes, modeling it as proving false. So it really is it's not a notion of computation that guarantees to produce values the way we are, law of the excluded middle really promises you that it will all finish and you will get a bit.
If you had a current processor, you could imagine trying both at the same time. It's seeing which one works. But the downside is that you can never trust anything the machine does in the meantime because you don't know which branch was actually the right one. So if you print something while you're trying to do this, that printing could should never have been printed because it was printed in the wrong branch.
Yeah. So it's I mean, if you're thinking this is weird, then good because it is weird. But I'm just trying to point out how traditional logic is mighty strange when you stare at it from a computational perspective. I mean, so the analogy here is that if you're trying to, what is said is, if you're trying to compute P, it is okay to suspend the process that computes P and give control to the operating system. So you can think of having a hypothesis which is a negation. is having a suspended process. Yeah? Because anytime you try to prove false and you know a negation, you can say, okay, I'm going to wake that process up. I'm actually going to go back to proving B. Yeah?
Sorry, I have a few questions on this. So, first one, the simple one, the DNA in set 1, is that the way to find time?
Yeah, so this is because we're quantifying over type, but over
Right.
So it's not set 1.
Okay. And the second one, is it possible to write out? Like, how would you write the polyclassical thing? The DNA well, yeah.
Well, yeah. So this is perfectly constructive, right? So here is the program that implements this.
Right.
If you're assuming something that's magic and you're never actually going to be able to provide.
Oh yeah, my issue is not like that. I don't believe that's logical at all. My issue is to translate that to symbols I understand.
So this says that if you assume this principle that you can delete double
Then
negation,
you get
then you can also decide for any
other way around.
property. Well, this D in the implies them.
Yeah, so if you assume lem first, then you get duplication. Oh yeah, yeah, duplication.
Assume that you can delete
Right,
negations, then that says that you can actually decide if P or not P is true.
Yes, sorry.
You can also do the other one, yeah.
So, like, I see you put your comment up there saying the DNA is unimplementable as lem. So, like, I guess in that instance, you could also do it like lem implies.
Right.
Yeah, you're right.
Should we do this one maybe?
Okay.
So so they are as bad as each other.
Yeah, so from there, I guess if you had something was you couldn't actually prove yourself, could you just take something that you can't also prove and then just use that to prove that it can't be proved?
Yeah, so that's what I tried to say with this. Yeah, so okay, if we done this, then we know that these two are implying each other. So they are
you
just
had
as
a
bad.
proof function.
And if you now had a third thing, you had a suspicion that I can't seem to prove this,
So you could take
then you could
excluded middle.
Yeah.
Just
Yeah, you can always say, okay, yeah.
if I could implement this, then I could also implement this through the middle.
Okay.
I know that this through the middle implies the halting problem, so I know that I can't implement that.
Right.
And all of a sudden the moon turns into green cheese. It's just, a good way, to show that something is not provable is to show that something really unpleasant was.
Okay, let's see if we can do this one as well. So we are assuming that we can decide P or not P, that's our left. And we want to show that if P is impossible, then P is true.
Not really.
Sorry, not P is impossible. So P plus bottom, that one get. Okay, so again, we have to start simply we are taking an argument.
Yeah.
So we assume not P, and then with P. Okay, any idea how we should proceed? We have to make use of our lem assumption, right? Otherwise we won't have to do it.
Let me just apply lem to NFP.
Well, we could just ask them if P or not P is true. Right?
I mean, if we're lucky, P is true, we're just not.
So I say, okay, what is lem of P? And it is this mu by the QQ. And now I can pattern match on QQ, right? Which is why I named it
Yeah.
such a.
So, I mean, it's just.
And we know that there are two cases. Either P was true or not P was true.
Yeah, I mean, this is it's just straightforward set pairing. That's it's like P, are you true or false?
And if it's true, then you're very happy, right?
Yeah, that's all right.
Now we just return the
If
P we
that's
have.
true,
If it's not true,
we're going to give you a kick.
we also know that P not being true is impossible. So it's NLP applied to MP. empty type. What could that be? It's nothing. So you see that in either case, either we get fraternity or the other case was actually really impossible to produce something on the empty type. So if we can decide if things are inhabited or not, then we can also do this impossible thing. Which means that if you want to prove that something else is not possible, then we can.
Just a similar pattern, just
Yeah, then we just choose the one which is easiest to reduce the problem to.
right.
Okay, so the summary here is that there are certain principles that you might have been taught in maths, but if you think about them from the point of view of actually implementing them on a computer, then they are just not possible. Because then you can solve the voting problem. But you can still do interesting things with them by assuming them. And then, I mean, it's still an interesting fact that they are implying each other, right? It's not the case that this is not implementable, so we can't even talk about it. You can still assume it and derive interesting facts.
So I mean, it's a different situation from, to some extent, the mathematicians are trying to figure out what God owns, whereas we're trying to figure out what bits we can make a computer disgorge. We are not in such a blessed state. We are humble. There are things we can't.
Okay, so we have about 10 minutes left. So let's talk. Yep.
Can I ask a question? Sorry.
Yeah, of course.
The width, I'm still unsure exactly what that's doing.
Which this one?
Yeah.
So this one is saying, okay, now I would like to pattern match on this expression.
Okay, that expression, the only option was.
And the type of this expression is empty type.
Yeah.
So that's the impossible absurd pattern.
Bring me this so I can look at it. Is what Wim does.
But I have none.
Okay, so 10 more minutes. Let's see if we can also deal with quantifiers. So we looked at and or and bottom and top, implication, etc. But in logic, there's also the statement that says that for every natural number something holds, or there is some tree such that this holds, etc. So we would also like to represent these things in our programming language. So let's start with for all. What does it mean to show that for every x in A, P of x holds? It should mean that if Colin wants to prove this, then he should be ready for every x in A that I give him, he should be able to give me back a proof of P of x, right? If Colin wants to show for every natural number P of n, then if I give him 17, then he should give me a proof of P of 17. If I give him 10 million and 3, then he should give me a proof of P of 10 million and 3, etc. So that sounds like a function which takes an A and gives you back a proof of P of A. That's exactly the kind of functions we were writing, where we named the thing. So let's see if we can give an example. Here is a function. It takes a natural number and gives back a proof that either n is even or suck of n is even. We're saying for every n in n, either n is even or n plus 1 is even. We might have to remember how is even was defined. So we said that 0 is even, suck of 0 is not even, and suck of n is even if and only if n is even. Okay, so how do we prove this? Well, we write a function of this type. How do we write a function of this type? We take a natural number. Now here, we have to produce something this type. Okay.
So it's good to notice that we're actually not just promising that every natural number is either even or we're more than that, we're promising to tell you which,
By going left, going right. Right.
and then handing you the actual evidence. So it's not a Boolean value function which says yes or no, what the question was. We're going to say it's even, I'll give you the evidence that it's even, or it's odd, I'll give you the evidence. Okay. We need to figure out how to get that.
Yeah. So the first thing we should ask ourselves is, can we now give something of this type? Can we commit to an output? Any ideas?
We can't get that.
No, if we don't know
I
what
don't know what the number is, so we,
we can't say, okay, I'm definitely going to go left all the time, or I'm definitely going to go right all the time, because depending on what that is, I sometimes have to go left. Or sometimes have to go right.
yeah, it's an important observation that you actually have to care what the number is to figure out whether it's even wrong.
Maybe we should end up re-implementing it.
No, this is an excellent question. I'll get there in a minute.
Yeah, we can compare at the end. But
Um,
okay, so I don't know what n is, so how do I figure out what n is? I'm going to pattern match on it. Then I'm going to get two pieces, it's either 0 or a successor. And now we can look at the 0 case.
3 years ago, however long, it's jumping on. Okay.
Okay, and then we see that if even of 0 was defined to be top, true, is even of sub of 0 was defined to be false, empty. So these things have now computed down to these things, right? And now it's becoming a little bit clearer where we should go. I think, right? We can either go left and win, or we can go right and struggle. So it asks auto to do it for me.
Yes, Control C, Control A. Yes, at this stage.
Okay, so if we look at this goal, we see that the left-hand side is even of sub n, but the right-hand side is actually already computed.
Yeah, if you just do load, does it pick the uncomputed version? Just so that we can see it happen? Yes.
Yeah.
So you can see we got a particular instance of the goal. We now have a double successor on the right, and that is computationally good news given the way it's particular compute factor is even now.
Okay, but if you look at the definition of is even, here we also had a special case for suck of 0, right? So it's probably a good idea to follow this structure. Match on n one more time. And here again, it's easy choice between impossible and trivial. And in this case, we now see that everything has computed. Before, if I just load, this is this horrible long thing, is even of suck n, or is even of suck n. But is even of suck n computes down to is even of n. And similarly, so if I just do a recursive call here, I get exactly what I want, right?
So now you can see that we're making a recursive call on some input that's definitely smaller, which is another way of saying we are entitled to an induction hypothesis for the smaller statement about a smaller number.
So you see what's going to happen if you apply this function to some complete number, such as 42, we are going to peel off 2 sucks over time, so then we're going to put it on 40, 38, etc., until we get down to the 1 case or the 0 case. And then we're going to return the thing.
So there's transferable lesson here. what did we do in order to get this proof to work? We looked at the number in such a way as to provoke the definition of is even to compute. So we had already a recursive definition of is even, and it's a terminating function. You know, when we do structural recursive calls. So if we can persuade it to take computation steps, we know we are going to be reducing to a smaller problem.
Well, there's always will a proof of something or one version of something, one version of the content. So it's always going to look the same. It's basically what I'm trying to say, because you've got the function, you've got the proof, and they look almost identical.
So not always, but a hell of a lot of theorem proving problems amount to poke the data in such a way as to make the computation happen. And for that, if your goal includes functions that have been defined recursively, then you go look at the definitions of those functions, because that'll tell you how to poke the data.
So we'll do more of this on Thursday, I think. But okay, let's take a few minutes more.
Yeah, I mean it's
Finish this. Yeah, should we just? Yeah. Okay, so one observation is that the implication we had before, A or B, is just the same thing as a universal quantification where we don't care about the proof. That's by looking at the types. So these are the functions which are non-dependent, these are the functions which we never overtalk. Yeah, okay, maybe we should brush it and we should just stop there.
Well, I think because remember, we had the opposite problem, so maybe you can get payoff from it, because A and B was defined to be A times B, which was the confusing non-dependent special case of the confusing concept of dependent pair. So we already see dependent pairs.
Right. Okay, fine. Then let's finish it. So, yeah, what is the proof of there exists an X and A such that P of X? Well, if you think about what would it mean to convince me of this fact, then I would only really be convinced if you showed me a particular X, and you showed me a proof that P of X holds for that particular X. Right? So that's exactly the type.
It's not this
This is yes wrong. Sorry.
Claims they have a proof that something is you're really fine to say, well, what is it then? I expect to have the thing handed over. And someone else like the accident choice. Only. No, I'm fine. There's the intuitionistic axiom of choice is a perfectly sensible thing.
Perfect. We don't have time for that.
Yes.
Yeah, so what is it? It's a particular witness, A and A, and a proof of P of A, which is exactly this dependent pair. Two things, the type of the second thing can depend on the first thing. So let's prove that there exists a natural number which is even. Okay, so just think of your favorite even natural number, which is 52. So what do I have to do in order to do this? Well, I have to give two things, right? A natural number, 42. And then here I have to give a proof that 42 is even, which just computes down to true. Whereas instead, if I try to show that 43 is my witness, then here I have to give a proof of false. It's not true. So it has to be an actual. And you also see that there can be many different witnesses of an existential proof, right? 42 is one witness, 18 is another one. And And they are both equally good in order to prove this, because there's proof that both of them are even in this sense. So there can be many different witnesses. And I guess okay, let's do this. So that's how you produce proofs that things are even. How do you use proof that something is even? Well, so if you want to prove something else, well, here you're asked to write a function of this type. Right? So you're given an argument of a pair type you can take apart into the two pieces. Right? So we're given some proof P, pattern match from P. We get two pieces, we rename it. Understandable, and we see that we're given and the proof of M is even. So now here, if we now want to prove that there is an M which is not even, then we could, for example, use Zuckerman here or something.
Yeah, so we both should be one.
Yes.
Yes.
And then here, annoyingly, yeah. Now we have to do a little bit more work to see which way this n actually was even. So we know that Zuckerman cannot be even. Probably the easiest way to do this is to look at exactly what n is. And here we say 1. Bottom implies bottom. Again. We see that we weren't given the case where n was 1. Because there is no proof that 1 is even. So we only have to consider this case. And in theory, we can do a test call here. So the point I want to make is that if you're given a proof that something exists, then you can have pattern match on it and you get access to the witness and the proof. That's how you use it.
That lambda function is only required because you want to do dots of anything.
Yeah, so sorry, that was a bit.
If you do it by the order of that, in the type description.
Right. So here,
Because I want to write just dependent sum and then just dots in the even. But you would need the end, don't you?
yeah, you need it because I'm really negating this statement.
Yeah.
So it's a function composition of this and nothing.
So you're one on the left-hand side, the fact that you don't have a function, the lambda function.
Yeah,
is
yeah.
just you.
So this
There is actually implicitly a function value.
this is the same thing as.
Okay. Cool.
But then by eta contraction, this is the same thing as yes. Yeah, it's not a vanity at all. It's like a name. Okay. Any final comments or questions from anyone?
Yeah. So okay, here's an example where out of the determination there are several ways to do this. So this one, once again, Fred was being pulled towards a particular choice that made a computation unfold.
So I wanted to make use of this proof that n was even. But if I don't know what n is, I don't know exactly what the proof is. But that proof was exactly the thing that allowed me to not deal with a Sacco zero case here.
I guess the other comment is that the one case didn't even show up, and that's this act of being a smart arse. It's okay, yeah. So you could manually fill in a one case, but it's got a brute false typing in it, so you could explicitly get rid of it like that. Actors say, "Oh, I'm not even gonna waste your time on that one." Sometimes it is a little bit worryingly too clever I am.
So every time it's the end, we would just replace that with an underscore, but actually have a need.
Which one?
The proof of busy.
This one. Yes, this one we're not using. This one we are using.
We're already using that to get it back into the function itself. So,
Yes, but it's still needed,
Okay.
right? I mean,
but we don't actually use it basically.
well,
Anything with that.
well,
Yeah.
I'm using it.
I realize, yeah, we're calling, okay.
And it's important what it is, right? I can't just say figure it out. It's not obvious that there is something to figure out here. There could be many different proofs of this. We don't know that yet. So we do use it in a central way.
Yeah.
Even though in the very end here we're not using it. Right? But we need to use it so that we know that it's important. We didn't try to do it as it was in a separate entity.
Okay, yeah. I wasn't realizing that. Yeah, but I read the one.
Because we are dealing with these pairs.
Yes, that's
Not
part of
just,
it. Yeah.
not just the numbers. Okay, but it's well time to stop.
Yeah.
So